Alright, thanks for watching. And today I would like to talk about the most important notion in topology, the one of a homeomorphism. Because a homeomorphism precisely describes how two shapes are similar or different. And in fact, you may have heard the saying that a coffee cup is just like a donut. Well, that's precisely the notion of a homeomorphism. Namely, it turns out both of them are homeomorphic. So without further ado, here's the definition. So definition, we see a function f from, again, either a topological space or a metric space is also fine, from M to N is a homeomorphism So careful, not the same as homomorphism, that's something different in abstract algebra, and not the same as anamorph, that's also something very different. So it's a homeomorphism if f is continuous, one-to-one, onto, so a bijection, and moreover, here's the important thing, the inverse is continuous as well. In other words, you can go from one shape to another without any tearing, without any jumping whatsoever. So really, you can kind of reverse the process, but in a way that's kind of continuous. Or I don't want to say smooth because it's not always differentiable, but that's the way you should think about it. So for instance, here are a couple of examples of homeomorphisms. Like for instance, well, f from the interval 0, 1 to 0, 2. Again, this is 0, 1 and then 0, 2. Kind of like that. Well, how can you go from one interval to the other? Well, for instance, you can double things. So f of x equals 2x. That's a homeomorphism because basically the doubling map is continuous, but then what is f inverse? It's the map 1/2 x, which is also continuous. So kind of what you're doing, you're just stretching the interval and then compressing it back. So in topology, they're pretty much the same shape. And in particular, what you can say that the intervals 0, 1 and 0, 2 are homeomorphic. It means they have the same shape, and in fact, remember, topology doesn't see distances. So for topologists, those are really the same thing. And another example, kind of maybe less trivial, but take, for instance, the circle, where it turns out it's homeomorphic to a triangle, because simply, here's a picture of a homeomorphism. If you take x, then f of x, it's just an orthogonal projection on that circle. And in particular, we're going from x to f of x that's continuous, but also kind of compressing the circle to get the triangle that's also continuous. And on the other hand, I believe, and that's very important, this is not a diffeomorphism. So because this has corners, whereas the circle does not have corners, this map is not differentiable. So be very careful. And then other examples, let's see. Yes, as I said, the donut and the cup of coffee are homeomorphic. I wish I had like some amazing demo for that, but not really. So, but the way I think you do it is simply you stretch the donut here, but you compress it on this part. So you get maybe something like that. So here's the hole, and then you get something like that, and then roughly you can slowly deform it into that mug, because you see this left part of the donut kind of becomes the mug part, and well, yeah, it kind of looks like a mug, more or less. I forgot the Play-Doh. Think of it as Play-Doh as well. I was like, pata mudle. How do you call that? All right, and then another more interesting example, because you're like, where are the formulas? Well, here's another interesting formula. So it turns out that the intervals 0, 1 and r are homeomorphic. Okay, which is very interesting because one is bounded, the other one is unbounded. So it's very important to understand boundedness is not a topological property. And first of all, here's the cool proof, which I really like. Suppose you have the interval 0, 1. So bend it a little bit that way. That's fine. That's a homeomorphism. And this is the real line. Well, just think here as someone being on top and just having a flashlight and looking at R. Well, in that case, you can associate this point with, let's say, this point, f of x in R, and so on and so forth. So in fact, every point here in the interval 0, 1 corresponds to something on that line. So I might be mistaken, but I think that's called stereographic projection. But as I said, if you want an explicit formula, well, first of all, notice you can go from the interval 0, 1 to the interval minus pi over 2 to pi over 2 simply by f of x equals, let me see, so I believe pi x minus pi over 2. So this makes it to be the interval 0, pi, and then by shifting it, you get pi x minus pi over 2, and you can check that the inverse function is also continuous. And how do you get from minus pi over 2 to pi over 2? Well, with the celebrated tangent function. So from minus pi over 2 to pi over 2 to r, you just take g of x be tangent of x. And what is the inverse? It's arctangent, which is continuous. And then how do you get from 0, 1 to r? Well, you just compose them, because the composition of two homeomorphisms is a homeomorphism. So you can check that. I think G composed with F is a homeomorphism. All right, so those are examples of homeomorphisms, and the question is now, what are some other topological properties that are preserved on the homeomorphisms? Well, a couple of ones are, for instance, compactness. So what are some topological properties? So we've seen boundedness is not one of them, but compactness is one of them. Namely, and here we don't even need the inverse function, but basically if K is compact and F is a homeomorphism, then F of K is compact. And actually it's quite nice because it allows us to rule out some sets that are not homeomorphic. For instance, the closed interval 0, 1 and R are not homeomorphic. It's kind of interesting because the open interval and R are homeomorphic. But the reason they're not is this is compact and this is not compact. Another property, connectedness. Namely, if C is connected and F is a homeomorphism, then F of C is also connected. And which again tells us something very interesting. It turns out that, for instance, let me see, the interval 0, 2 pi and the unit circle in R2 are not homeomorphic. Okay? And you're like, wait a moment, aren't those two connected? Yes, they are, but notice the following. So this is the circle, and this is the interval, 0, 2 pi. However, here's the thing. You can actually show that if you remove a point from this and you remove a point from this, then they would still be homeomorphic. So homeomorphism doesn't matter if you remove a point. But here's the thing. If you remove a point from S1, this is still connected. But if you remove a point from the interval 0, 2 pi, it's not connected anymore. Connected and not connected. So again, to reiterate, if both of those were homeomorphic, then removing a point would not destroy the homeomorphism, but the problem is here, this circle with a point removed is connected, but the interval with a point removed is not connected. So that's the issue. And another property, of course, the most important one in topology, is openness and closeness. So, openness, open and closed. So this is, for instance, why the open interval 0, 1 and the closed interval 0, 1 are not homeomorphic. Because, well, this is open, so this should be open, but they're not, but it's not. And let me just quickly prove this. So suppose U is open. Okay. And what we want to show F of U is open. However, what is F of U? Remember, F is a homeomorphism, so it's invertible. So F of U, it's, let me see, it's F inverse of U. And here's the cool thing. So F inverse of U is continuous because F is a homeomorphism. And remember, for continuous functions, the pre-image of an open set is open. So U is open. Okay. F inverse is continuous, so the pre-image of F inverse of U is still open. So the whole thing is open, and therefore F of U is open. And exactly the same argument for closed sets. All right, last but not least, I do want to do a couple other neat facts about homeomorphisms. So other facts. Because you might be like, well, why do we even need F inverse to be continuous? Doesn't it automatically follow? Well, it turns out that no. You could have F to be open, so to be continuous, and 1 to 1, and onto, but F inverse not continuous. Okay. So the point is, this is very important, and let me give you an example. Take, for instance, the interval 0, 2 pi, this one, and the unit circle. Okay. I want to give you an example of a map that's, again, continuous 1 to 1 and onto, but whose inverse is not continuous. Well, simply, given t here, consider the point cosine of t, sine of t. Okay? So in other words, let f of t be a cosine of t sine of t, and you can show it's continuous, no problem. It's 1 to 1, no problem. And it's onto the circle, no problem at all. However, I'm claiming that the inverse is not continuous. And for this, consider the point 1, 0, and consider the point cosine of, I believe, pi over 2 pi minus 1 over n, and sine of 2 pi and minus 1 over n. So consider if you want Sn to be a cosine of 2 pi minus 1 over n and sine of 2 pi minus 1 over n. Right. Then on the one hand, Sn by definition converges to cosine of 2 pi and sine of 2 pi, which is 1, 0. Then Sn converges again to a cosine 2 pi, sine 2 pi, which is 1, 0. But then what about the inverse? So the problem is, but f inverse of Sn, again, what is f inverse is just the angle here, but the angle for Sn is just 2 pi minus 1 over n and 2 pi minus 1 over n. So f inverse of Sn, it's 2 pi minus 1 over n, which converges to 2 pi. On the other hand, which angle does 1, 0 correspond to? Well, since we have the half-open interval 0, 2 pi, f inverse of 1, 0 is just the angle 0. And f inverse of 1, 0 is just 0. So what do we have? Even though Sn converges to 1, 0, f inverse of Sn, which goes to 2 pi, does not converge to f inverse of 1, 0. Because you see, this limit is 2 pi, but this number is 0. Therefore, f inverse cannot be continuous, because if it were, this would be true. On the other hand, there are some cases where the inverse is continuous. So, for instance, we've seen that in another video. If f, let's say from an interval to f of an interval, is 1 to 1 and continuous, then f inverse is continuous. So f is a homeomorphism. But that's very specific to R and to intervals. But in general, what's nice is that if f from a compact set to, let's say, any f of a compact set, so if f from k compact to f of k is continuous and 1 to 1, then f is a homeomorphism. In other words, f inverse is continuous, and again, that's what makes compactness so nice. And the reason for this is, well, to check it's a homeomorphism, we just need to check that f inverse is continuous. And which just means the pre-image of any open set is open, or equivalently, the pre-image of any closed set is closed. So let C be any closed set in this set, so in K, okay, and we need to show f inverse of C is closed, because again, that would show that f inverse is continuous. But here's the thing, And that's what makes compactness so nice. Well, if C is a closed subset of K, since K is compact, C is compact. So since C is closed and K is compact, this implies C is compact, but since F is continuous, this implies f of C is compact. And in particular, if it's compact, it's closed, so f of C is closed. And therefore, we're done, because f of C, that's just f inverse of C. And therefore, such maps are open or closed, or in this case, homomorphisms, whatever you like to call them here. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.